Okay, sorry guys for kept you waiting with the second part of the test, section B, but I was working on a paper I was writing, so I didn't have time to film this video. So let's jump right in. One thing I forgot to mention is that if you guys if you guys notice here, this question, for example, 11, gives you 4 marks. So the rule of thumb is that it should take you 4 minutes, okay, roughly. If it gives you 6 marks, 6 minutes. If it gives you 9 marks, 9 minutes, etc. So it gives you a sense of how much time you need to devote on a problem, and it also tells you how difficult the problem is sometimes. And another thing is that if you don't know how to work on a problem, skip it and find problems that you can work on and then return to the ones you skipped later. That's how I do things. So let's read question 11. During an experiment in 1934, Chadwick fired alpha particles at beryllium atoms. Carbon atoms and neutral particles with the same mass as protons were produced. This led to the discovery of neutrons. We discussed this in the video where we talked about nuclear reactions, I think, so you might want to look into that anyway. So complete the equation for this process. The alpha particle has a mass number of 4 and an atomic number of 2 because it's the helium-4 nucleus, so it has 2 protons, 2 neutrons. Okay, carbon. Okay, they tell us that a neutron is produced that has no charge. So it has a mass number of 1 and charge is 0. So the atomic number is 0. So we have to match these numbers. 4 plus 9 is 13. So we need a 12 here and a 6 here. But of course, you might remember that carbon is 6. So let's do part B. A book about the Chadwick experiment includes the following statement. Chadwick's experiment established that the neutron was a new fundamental particle and not an electron and proton joined together as suggested by Rutherford. Criticize this statement with reference to the structure of the neutron. So what you can write there, this might reply to the problem, but my response, but you can look into the mark scheme as well. So neutrons consist of 3 quarks, and you can specify them, one up quark, one d, and another d. So the up quark has a charge of 2, and 2 d quarks have a charge of minus 2/3 plus 2/3, 0, okay? So they consist of 3 quarks, therefore it's not consisting of a proton-electron pair, and it's not a fundamental particle. So pretty much you have to write everything you know about neutrons here, okay? So let's move to question number 12. A student investigated the charging of a capacitor. She measured the current in the capacitor circuit as the capacitor charged through a resistor. Add to the diagram to show a suitable circuit for measuring the current as the capacitor charged. So since we are given the capacitor and the resistor, we can add an ammeter because we will need that to measure the current, right? And we need a battery to charge the capacitor. So we can add a battery like this. And I think this is the A-level style. Okay, so this is the voltage. All right, part B. The graph shows how the current in the circuit varied with time as the capacitor charged, okay? So this is an exponential decay curve, pretty much. The resistance of the resistor is 5.1 kilo ohms. Show that the capacitance of the capacitor is about 0.02 farads. So to do that, we can calculate, first we can calculate the lifetime of the capacitor, and we can do that by finding that, so this is one solution. I guess there are others in the mark scheme. So we have that R is 5.1 kilo ohms. And from the graph here, we see that this point, that's I naught, the initial current. So let's write it here. I naught is, if we read it off, it's about 2.4 milliamps. Okay. and 0.37 of I naught, which is the current left in the capacitor after one lifetime, is 0.88 milliamps. So if we go back to the graph, 0.8 is right, let me see. So 0.88 is about 0.9, so this is 0.75, 80, 85, 90, so that's the point, somewhere there, okay? So that's 0.37 I naught, and if we go down, we can read off that that's 75, 80, 85, 90. Okay, so that's about 90 seconds. So that's the lifetime of this capacitor. Why? Because we know that in one lifetime, 63% of the current is gone, or 37% is left. So since tau, the lifetime is 90 seconds, and we know that that's equal to the resistance times the capacitance, we can solve for C. So 90 seconds over 5,100 ohms, which is the resistance, gives us 0.018 farads, which is about 0.02 farad, okay? Which is what they ask. So we are good. Part 2, calculate the charge on the capacitor when it is fully charged. So one way to do that is to realize that the initial current is equal to the initial voltage over the resistance. So the voltage can be calculated as I naught times R, which gives us 12.24 volts. And then we know that Q naught, the initial charge, is equal to the capacitance times the initial voltage. And so that gives us the initial charge is 0.22 coulombs. And the final part is calculate the energy stored by the capacitor when it is fully charged. So the energy is 1/2 C times V squared. It's also Q squared over 2C, and so on and so forth. We will use this and find 1.35 joules if we plug in the numbers. I'm not showing the numbers because it's gonna get tedious. I assume that you guys have a calculator so you can plug in for yourselves. Now, let's go to question 13 and check my solutions. A student investigated the forces involved in circular motion using a coin placed on a plastic disc. So this is the plastic disc, we see it here, and this is the coin. Let's use a different color. Let's use maybe orange for the coin, sorry. Okay. The mass of the coin was 8.8 grams. The diameter of the disc was 30 centimeters. Okay. The student determined the maximum frictional force between the coin and the disc by tilting the disc as shown. The edge was raised by 6.3 centimeters before the coin started to slide. Show that the maximum frictional force was about 0.02 newtons. So let me raise this. Let's write down the forces involved. We have the reaction force, m times g, right? And this angle, if this angle is theta, then let me redraw this. So the perpendicular force and m times g, and then if we extend this angle over there is also theta. I hope you can see it. So the angle over there is theta. Why? Because this side is perpendicular to this side, and this side is perpendicular to this side. So therefore, if this is theta, this is also theta. Now, we can analyze the forces in this axis, right? So in the axis that is parallel to the plane. So we have the component of gravity in that direction, friction in that direction. And in this direction, we have mg sine theta, okay? And the way to tell this is that mg cos theta will be this component, which is adjacent to the angle, to this angle theta. This component is not adjacent to the theta, so it's mg sine theta. This is how I remember things, okay? So if we set the frictional force equal to mg sine theta, and since mass is 8.8 times 10 to the negative 3 kilograms times g, which is 9.81, times sine theta, which is the sine theta is equal to 6.3 centimeters over, they give us the length of the disk, right? So 30 centimeters, okay, 30. So if we plug in, we find 0.018 newtons, which is about 0.02 newtons, okay? Part B. The student placed the disk on a horizontal turnable and placed the coin on the disk, as shown below. The disk rotated at 45 revolutions per minute. Calculate the angular velocity of the disk. So we have 45 revs per minute, okay? So omega is 2 pi times the frequency. So 2 pi times 45 revolutions per minute, which is 45 over 60 seconds, right? So that's 4.71 radians per second. Simple. Part 2. Let me see. When the student placed the coin near the center of the disk, the coin remained in position and rotated with the disk. When the student placed the coin at the edge of the disk, the coin slid off the rotating disk. The student estimated that the closest the coin could be to the edge of the disk without sliding off was about 5 centimeters. Deduce whether this was a suitable estimate. You should assume that the maximum frictional force is 0.02 newtons. So for this one, we can use the fact that the centripetal force should equal m omega square times r with and r. Actually, let's use a different r. So for here, let's use just r, lowercase r. And the radius of the disk is 15 centimeters. So 5 centimeters off the edge means r is 10 centimeters, right? So since fc is m omega square times r, and fc we assume to be the maximum frictional force is 0.02 newtons. So let's plug in. The mass is 8.8 times 10 to the negative 3 kilograms. Omega is 4.71 squared, it was calculated earlier, and r is 10 centimeters, so 0.1 meters. If we plug in, we get 0.019 newtons. So the estimate is suitable, okay? Since 0.019 newtons is about 0.02 newtons, so the student is correct. Moving on to question 14. According to the standard Quark-lepton model, most of the visible matter in the universe consists of quarks and leptons. The table shows 6 types of quark and their charges. Okay, so we have up charm and top with plus 2/3 E charge, and down strange and bottom have minus 1/3 E. Okay, state the quark structure of baryons and of mesons. So the quark structure of baryons consist of 3 quarks, and mesons consist of 1 quark and an anti-quark. Okay, this was discussed in the theory. Scientists, part B, scientists have proposed the existence of particles called leptoquarks. Leptoquarks have baryon number and lepton number and decay to quark and a lepton. One type of leptoquark has charge plus 5/3 E. Determine the baryon number and the lepton number for this leptoquark. Include the suggested quark and lepton in your working. So we have a charge of plus 5/3 E. Okay, so one way to achieve this is to couple an up quark with a positron. This thing will have a charge of plus 5/3 because we will have 3/3 coming from the positron and 2/3 coming from the up quark. and it will have a baryon number of 1/3 because remember when we discussed quarks by themselves have a baryon number of 1/3. Therefore, when we are dealing with a baryon, 3 times 1/3 gives us the baryon number of 1. Okay, same for mesons. Since a quark has a baryon number of 1, an anti-quark has the opposite baryon number, so minus 1/3. So we get 0 baryon number for mesons. So, but here we get the baryon number of 1/3 and a lepton number of -1. Okay, be careful with that because this is a positron, and positrons have a lepton number that is opposite to the lepton number of electrons, which is 1. Another combination is a charm quark with a positron. So the situation is the same. Charge 5/3, baryon number 1/3, lepton number -1/3. We can also get a top with a positron. So the top quark has a charge of +2/3. So this also works. But what do they say? One type of leptoquark. Okay. Okay, other combinations are to use muons. So muons with, you can use a U quark and a positive muon, or a charm quark with a positive muon, or top with positive muon, right? Yes. And what else can we have? We have electrons, muons, and the next ones are and we can also have combinations with the tau, right? I forgot that. So tau and, sorry. And we can also have an up quark with a tau plus, a charm quark with a tau plus, or a top quark with a tau plus. Okay, so these are all the combinations you can have of leptoquarks. Moving on, part 3. Scientists search for new particles using high-energy particle collisions. The highest energy particle collisions involve colliding protons moving in opposite directions, each with energy 6,800 GeV. It is estimated that 11% of the total energy of a collision could be converted to the mass of a new particle. Show that the maximum mass of a particle that can be produced is about 3 times 10 to the negative 23rd. So here we are told that 11% of that energy of 6,800 GeVs, which is 10 to the 9 EVs, and 1 EV is 1.6 times 10 to the negative 19 joules, is available to be converted into energy. Okay, so let me write this down. So this is joules. If you multiply, you get 2.39 times 10 to the negative 7 joules. So this is 1 EV, this is the 1 G. Okay, and let's see how much mass does that energy correspond to. Remember, mass and energy are equivalent. So delta E is delta M times C squared. So delta M is whatever we found there, which is delta M is delta E over C squared. So 2.39 times 10 to the negative 7 over 3 times 10 to the 8 squared. And if you plug in, we get 2.66 times 10 to the negative 24 kilograms, which is about 3 times 10 to the negative 24, which is what they ask. Okay, so this works. Now, leptoquarks have not yet been observed. This is the thing with particle physics, guys. To give you like a personal perspective, I always loved particle physics, but there are so many crazy theories proposed that were never verified by experiments. So that's that. Okay, so let's move on. Suggest why leptoquarks have not yet been observed. So a simple answer is that their mass is probably higher than 3 times 10 to the negative 24 kilograms. Therefore, even though we use powerful colliders, we haven't found them, but most probably they just don't exist and the theory is wrong. But anyway, don't write that, okay? Write this. All right, let's now work on problem 15. An air table has a surface with many small holes. Air is blown through the holes. Plastic pucks can move freely over the table on a cushion of air. The photograph shows the surface of an air table with 2 pucks on it. So we see the 2 pucks over there. So let's see, some students used the air table to investigate conservation of momentum. Explain how using this air table ensured that momentum was conserved in collisions between the pucks. So this is a 2-mark question. So it's kind of a simple one. The principle of conservation of momentum says that we shouldn't have an external force. In this case, the external force will be friction, which is eliminated because of the air cushion. So we're going to write friction is minimal, thus there is no external force acting on the 2 pucks, thus momentum is conserved. Now, that's it. Let's move to part B. The students observed several collisions between 2 identical pucks, A and B. One puck was stationary before each collision, okay? So puck B was pretty much stationary, okay? They noticed that after each collision, the 2 pucks seem to follow paths at 90 degrees to each other. The diagram below shows one of their collisions. So this angle is assumed to be 90 degrees, okay? The students recorded the following data for this collision. The initial momentum of A, which we're going to call PA, the angle A, so which is that one, the final momentum of A, we're going to call that PA prime, okay, P subscript A prime. And yeah, let's go see the question. So part 1, deduce whether the angle between the paths of the 2 pucks after the collision was 90 degrees. You should use the principle of conservation of momentum. Okay, so this is going to be a little bit involved, but let's try to make sense of this. So I like when I work with momentum problems, I want to separate the before the collision situation with the after, which is done for us automatically since they give us the nice diagram here. Okay, so let's go write down the momenta before and after. So before we have only PA because B is stationary, okay? And after the collision, we have PA prime and PB prime, okay? I use the prime for the after the collision situation, okay? So we see immediately that these 2 guys can be analyzed into a horizontal component, which is going to be PA prime cosine of the angle A, which is given to us, and PA prime sine of A. Similarly, for the other puck, we will have PB prime, and this angle is now B, cosine of B, and the other component is going to be, let me erase this by the way, and the other component is going to be PB prime sine of B. And the way I work these things out is whenever I have an angle theta and some vector, let's say P, the x component is going to be P cosine theta, and the y component is going to be P sine theta. So the side, the component that touches the angle theta is the cosine theta, and the component that doesn't touch, you see that the angle theta is here. So this component does not touch the angle, right? In a sense. So that's P sine theta. That's the trick I use. Okay. Deduce whether the angle is 90 degrees. So we have to work with the algebra here. So unfortunately, this is going to involve some math. So for the y-axis, the momentum before is 0. So therefore, the momentum after should also be 0. Therefore, the 2 components need to be opposite. Let's take A prime to be the positive one since it points up. So 0 should be equal to PA prime sine of A minus P B prime sine of B. Okay, from this one we can get that PB prime is equal to PA prime sine of A over sine of B. Okay, and in the x-axis, the momentum before is simply PA, and this should be equal to the momentum after. Since both components point to the right, they should add, okay? So this should be equal to PA prime cosine of A plus PB prime cosine of B, okay? And if I bring, let me see, I can take PA prime cosine of A to the left hand side, and this is equal to PB prime, but I can insert this P prime, this PB prime from the Y condition, right? So PB prime is PA prime sine of A and then over tangent of B. I went a little bit fast, but this is because you have a sine B in the denominator and a cosine B in the numerator. So sine over cosine gives me tangent of B, all right? And therefore, the tangent of B, and I'm running out of space, so I'm gonna use a new page, okay? So the tangent of B is equal to PA prime sine of A over PA minus PA prime cosine of A. So therefore we expressed everything in terms of quantities we already know and they are given to us. And if we plug in, we find that this is equal to 1.59. Taking the inverse tangent gives us B equal to 57.96. Therefore A plus B is 90.96 degrees. Therefore, indeed, they move at 90 degrees. Okay, and the last part is to deduce whether the collision was elastic. For elastic collisions, we additionally have conservation of kinetic energy, so we have to calculate PA squared over 2m, which is the kinetic energy before, and PA prime squared over 2m plus PB prime squared over 2m, which is the kinetic energy after, okay? So if we set this two equal to each other, we see that PA squared over 2m must equal PA prime over 2m plus PB square prime squared over 2m. The 2m's cancel, so all you have to do is to calculate PA squared, which is 2.12 times 10 to the negative 3 kilogram squared meter squared over second squared. And we also have to calculate PA prime squared plus PB prime squared. And this ends up being 2.14 times 10 to the negative 3 kilogram squared meter squared over second squared. These two are equal, therefore the collision is elastic. Question 16. Scientists at CERN are planning an upgrade to the LHC called the Large Hadron Electron Collider, the LHEC. The scientists plan to use a linac to produce high-energy electrons. Collisions between these electrons and high-energy photons will allow the structure of protons to be investigated. Question A. The high-energy electrons produced will have energies of 60 GeVs. Show that these electrons will be traveling at relativistic speeds. One way to do this is to use the classical kinetic energy and show that the electrons will have an impossibly large speed. So let's go see what I mean. So let's set 1/2 mv squared equal to 60 GeVs. So we have that v should be the square root of 2 times 60. GeV means 10 to the 9 EVs. 1 EV is 1.6 times 10 to the negative 19 joules. And then we have to divide this with the mass of the electron, which is 9.11 times 10 to the negative 31 kilograms. All right, so let me write this. This is G, sorry. Oops. This is G. This is 1 EV. etc. Okay, I hope this is clear. If we do this calculation, we will find that the velocity should be 1.45 times 10 to the 11 meters per second, which is larger than c. Therefore, this is impossible. And the true answer is that, I'm sorry. And the true answer, oops. Is that the electrons are relativistic. All right, part B. The diagram shows the start section of a linac and the end section of a linac. So this is the start section, and this is the end section, okay? So I guess what they want you to notice is that in the beginning, these drift tubes get progressively larger, but at the end, they are about the same, okay? And why does this happen? Because by the end of the linac, the electrons have relativistic speed, so their speed does not change by too much between drift tubes. But let's go see what the question is actually asking. Explain how a linac produces high-energy electrons. You should refer to the AC supply and to the length of the drift tubes in each section. So my attempt at the solution is the following. An AC voltage with constant frequency is applied between the tubes. Okay, this allows for the polarity to change signs, so alternating between positive and negative pretty much. Okay, electrons are accelerated by the positive voltage. When they reach the middle, by the way, I made a mistake here, should be voltage. So when they reach the middle of the drift tube, let me see, of the drift tube, the polarity changes and it now repels the electrons which accelerate towards the second tube. Okay, since the velocity increases, the length of the tubes should increase. To account for the increased velocity of the electrons. All right. Okay, and one more thing we need to add. Let me create a new page. So I was saying that since the velocity increases, the length of the tubes should increase to account for the increased velocity of the electrons. As the electrons spend the same amount of time in each tube. Okay, as electrons approach c, the speed of light, their v does not change, Thus, at the end, the linac has constant length tubes. Right? Okay. And we are left with part C. This is a 3-mark question, so it's not trivial. Explain why high energies are required to investigate the structure of protons. So we can write that the proton has a diameter of about 10 to the negative 15 meters, or 10 femtometers. Thus, we need particles with small lambda. Since lambda is h over p, this is Prince de Broglie's formula, okay? The larger the momentum, actually let's be brief. So since the wavelength is inversely proportional to the momentum, if p is large, lambda is small, okay? So with higher momenta, electrons can more easily penetrate the proton and transfer momentum. And that's the answer. All right. Question 17. Scientists are developing safe methods for removing old satellites from orbit. Some scientists plan to use electrostatic forces. A spacecraft will fire a beam of electrons at the satellite. This will give the satellite a negative charge and the spacecraft a positive charge. There will be an electrostatic force of attraction between the satellite and the spacecraft. The spacecraft will then move away, taking the satellite with it. Okay, question A. The diagram shows the electric field around the spacecraft X. So this is the spacecraft and the satellite Y, okay? Let's erase that. And the satellite Y when they have equal and opposite charge. You may assume that the spacecraft and the satellite are both spherical and have the same diameter, okay? Question A, part 1. Add dashed lines to the electric field diagram to show equipotentials at intervals of equal potential difference. Okay, equipotential lines are perpendicular to electric field lines. So what you can do is start with the middle. Okay, so this is an equipotential surface at intervals of equal potential difference. All right, so something like this. Okay, so the idea is that these equipotential lines are perpendicular to electric field lines. And I remember when we say that equipotential surfaces grow apart as we move away from a charge. So this is what we will do. So the next one will be somewhere here. And this will be ellipses, guys, okay? So the idea is that I'm drawing lines that are perpendicular to these electric field lines, okay? If you can see that. So the next one will be further out and it will look like this maybe. And I don't know, it will close to a farther distance, maybe something like that, okay? And the same is true from the other side since these guys are symmetrical, okay? So something like this, okay? So these are equipotential lines. Now label the equipotential that represents 0 voltage. So this is going to be exactly in the middle between the two charges, okay? So V 0 volts in the middle, okay? And let's move on. Part B. After some time, the charge on the spacecraft will be 1.5 times 10 to the negative 6 coulombs, and the charge on the satellite will be minus 1.5 times 10 to the negative 6 coulombs. Calculate the minimum energy in joules required for an electron leaving the surface of the spacecraft to reach the surface of the satellite. Assume that the charge on each object does not affect the potential at the surface of the other object. and the radius of both is 2.5 meters. So we're given that Q of the craft, the spacecraft, is equal to Q of the satellite equal to actually the absolute value, the absolute value is the same, okay, because they are opposite charges, okay, and the radius is 2.5 meters. So the potential of the craft is 1/4πε0 times the charge over the radius, which is 5,400 volts if we do this calculation, okay? So I calculated the potential at the surface of the spacecraft. Therefore, the potential at the surface of the satellite is going to be the opposite of that, so minus 5,400 volts, okay? So if we go back here, we are calculating the potential right there, okay, and right there, since we are giving the charge and we are giving the radius, okay? This is the radius. So now delta V is going to be 5,400 minus of 5,400, which is 10,800 volts. Therefore, we are asked to calculate the minimum energy in joules required for one electron to leave the surface of the spacecraft and reach the surface of the satellite. So the electron is going to travel from here to there or the other way around, because I forgot. So wait, X is the spacecraft. So am I correct? Yes. So an electron leaving this guy and traveling to the other guy. So this is given by Q times delta V, and the charge of an electron is 1.6 times 10 to the negative 19 coulombs times 10,800 joules per coulomb gives us 1.73 times 10 to the negative 15 joules for one electron, okay? Let's go to part 2. The spacecraft moves to a new position, taking the satellite with it. The distance between the satellite and the spacecraft remains constant, so the electrostatic force is constant. The scientists estimate that the satellite could be moved a distance of 300 kilometers in about 60 days. Deduce whether this estimate is correct. Assume gravitational forces are negligible and the satellite is initially at rest. The distance between the center of the satellite and the center of the spacecraft is 20 meters. The mass of the satellite is 2,500 kilograms. So let's calculate the electrostatic force, first of all. So we have a satellite of a radius of 1.5 meters and a spacecraft, and this distance is 20 meters pretty much, and I'm gonna need a new page to work this out. So the force between them, since they have a charge Q and another charge Q, is going to be Q squared over 4πε0 r squared. We don't care about the sign because it's gonna be an attractive force. So this is also equal to K Q squared over r squared, where K is 1 over 4πε0. If we plug in numbers, 9 times 10 to the 9 times 1.5 times 10 to the negative 6 squared, which is the charge, and over 20 squared gives us 5.06 times 10 to the negative 5 newtons. Okay, so this force is gonna accelerate the thing, right? So force is mass times acceleration, so we need to find the acceleration as force over mass. So this is the force is this, the mass is 2,500 kilograms, so 5.06 times 10 to the negative 5 over 2,500 gives us 203 times 10 to the negative 8 meters per second squared. And now we have to use Suvat equations. So S is u, the initial velocity, times t, plus 1/2 at squared. The initial velocity is 0, so we cancel that term. And the acceleration is 2.03 times 10 to the negative 8 over 2. and then we have the time as 60 times 20, so 60 days times 24 hours times 60 minutes times 60 seconds, and the whole thing squared gives us 272.8 kilometers, so about 300 kilometers. So this estimation is actually correct, surprisingly. Right? Question C. In reality, the magnitude of the positive charge on the spacecraft may be greater than the magnitude of the negative charge on the satellite. Suggest why. So it's a 1 mark question, so you can guess some things. So some electrons don't hit the target. Don't hit the target, because remember, we shoot electrons at the satellite. Okay. Maybe the UV rays from sun lead to electron emission, etc. You can check the mark scheme for other questions, for other answers. So this was question 17. Now question 18. In some car engines, the power is provided by burning a mixture of fuel and air. The photograph shows a spark plug. You've probably seen those in old cars usually. The spark plug creates a spark that ignites the mixture. A very high potential difference across the gap in the spark plug is needed to produce the spark. The very high potential difference is produced using the arrangement shown in the diagram below. Okay, so we have a primary coil and some voltage provided to it with a battery, and a secondary coil and a gap. Okay, so the secondary coil is wrapped inside the primary coil. So, and there is also a core. The switch is closed and the current in the primary coil increases to a maximum value. The switch is then open and the current falls to zero almost immediately. The secondary coil produces a large potential difference, creating an electric field strong enough to cause a spark across the gap. Explain how a potential difference is produced across the secondary coil when the switch is open. So here we will write the following. There is a sudden decrease in the magnetic flux through the secondary coil. So how is a magnetic flux present? When the switch is closed, because we have the primary coil wrapped like that and the current flowing like that, okay, I'm sorry, then there is a magnetic field B produced inside the coil, okay? The moment you open the switch, okay, and that's the open position, by the way, the moment you open the switch, the current drops to zero, therefore the magnetic field flux, the magnetic flux goes to zero as well. So let's finish this according to Faraday's law. Let me use a black pen. So according to Faraday's law, an EMF is produced because we have a closed loop. An EMF is produced, comma, and because we have a closed loop, a current is also produced. Okay, let me use a new page. A current is also produced. Okay, the initial magnetic field is created in the primary coil, which is what I just explained. In the primary coil, due to the current passing through it. Okay, so you close the switch, okay, then there is a current in the primary coil that produces this magnetic field, and then when you open the switch, the magnetic flux in the secondary coil drops, and therefore an induced current is produced, which produces the spark in the gap. So this is the explanation, pretty much. Now, part B. The distance across the gap in the spark plug is 0.75 millimeters. Calculate the electric field strength in the gap when the switch is open. Assume the electric field in the gap is uniform, and they give us the magnetic flux density, the number of turns in the secondary coil, the diameter of the secondary coil, and the time for primary current to fall to 0. So the electric field is given by the voltage over the distance, and the voltage is equal to the amp over the distance, and then the amp is given by the change in the flux linkage over delta T, which is equal to N, the number of turns, times B times A, which A is the surface area, over delta T. So if we plug everything in, we are given everything. We have 30,000 times 0.34, which is B, times pi, times 16 times 10 to the negative 3 squared, which is the diameter of the secondary coil, over the time, which is given, we have 4 here because you're given the diameter, and the diameter is radius over 2, so that's where the 4 appears from. And then the time is 2 times 10 to the negative 5. So the amp is 102.54 kilovolts, and then the electric field is then equal to this amp over the distance, so 102 times 54 times 10 to the third over 0.75 times 10 to the negative 3 gives us 136.7 times 10 to the 6 volts per meter is the electric field strength. Okay, and the last part, C. When the switch in the circuit is closed, the current increases to a maximum value as shown. Explain why the current does not increase to its maximum value instantaneously. You should refer to Lenz's law. Okay, so when the switch is closed, okay, a magnetic field starts to build in the primary coil, okay? Because B changes with time, an amp is generated in the coil. I'm talking about the primary coil now, okay? That opposes the reason that created it. And what's the reason that created this magnetic flux density? The increase in the current, which is the current increase, okay? So, so this amp is opposite in polarity than the battery. So the current increases slowly. When B is constant, okay, so in this part pretty much, there is no change in phi. Thus, no amp, so I becomes maximum. So to make it clear, if we go back here, what's happening is that when you close the switch, the magnetic flux density starts building in this primary coil, okay, this guy pretty much. And because the current increases slowly, the magnetic flux B changes with time, which produces an electromagnetic force in this primary coil, which acts like a battery in the opposite polarity than this battery pretty much, okay? And this is what makes the current increase slowly, okay? Eventually that induced EMF goes to 0, and that's the answer. So this is it for the first video where we talk about the past paper. I hope you like it, guys. I will expect to hear your thoughts in the comments.